Lecture 14 continued, chemical bonding continued. All right. So remember yesterday, or Monday rather, we were talking about how melted salt actually can conduct electricity, right? And I know isn't there? I think there's a group in this. I think there is a group in here that's doing salt stuff today, uh, and I brought multiple types of salt for them. So you're welcome, whoever you are. Um, but yes. So interestingly enough, melted salt conducts electricity. Very similarly, though, salt in a solution can also conduct electricity, right? So the reason why, for example, when you are in the bathtub, right, and you're watching TV while you're in the bathtub, and it's like over the wall, right where your bathtub is, and the TV falls into the bathtub and you get electrocuted, right? The reason why that happens is because you have sweat, right? And most people don't realize this, but when they're in like a hot shower or a hot bathtub, they sweat, and that sweat goes into the water, making the water more salty than it normally would be. It also has the sediment from the wonderfully dirty water that's in Fort Worth and in Arlington and in Dallas, and all that stuff makes it so that electricity can be conducted through a solution as well, right? So aqueous solutions in which ionic compounds have been dissolved also conduct electricity, right? So that's very important for you to know because I might ask you a question, which of the following forms of salt can conduct electricity? And if I just have like powdered, table salt there, is that going to conduct electricity? No, right? But melted salt and salt that has been dissolved in solution, salt that has been dissolved in solution, how much you want to bet the person that is parking right now, they're the twins? So Ashley and a lady. I bet you that's who that is coming up right now. Anyway, I don't know if it's them or not. They're still parking. Anyway, um, but yeah, so only melted and solutions of salt will conduct electricity. But if it's just the powdered salt that you put onto your eggs in the morning, then it's definitely not going to conduct electricity. Okay, so that's important to know. Okay, um, there. Okay, so there's this thing here, right, where we call it the stock system. I don't know why they call it the stock system, but the stock system is basically this: the metals, which I don't really care much about, so I don't even ask you much about this, but I just want you to know, the metals that are in the middle here, the transition metals, they're called transition metals or the stock metals because they can actually lose more than one type of electron. Like they can lose one or two or three electrons. Okay. Um, that's very different from the other metals we talked about, right? Because we talked about how the alkali metals lose one electron, the alkali earths lose two electrons, right? Whereas the halogens gain one, the chalcogens with the oxygen right there gain two. But the funny thing is the ones in the middle, these transition metals here, they actually lose more than one, right? And so since they lose more than one, you get things like copper one, where copper here has a plus one charge, or copper 2, right? Where copper has a plus 2 charge. And so in chemistry, we denote these separate different charges by having the Roman numeral. So copper 1 is a copper with a plus 1 charge. It's got a very special name, and that's cuprous, right? And then copper 2 here, cupric, right, has a plus 2 charge. So it's capable of losing 2 electrons. Okay, capable of losing 2 electrons. Cool stuff. Cool stuff. Gold here can lose one, or you lose three electrons. So that's gold one, gold three. And then, so this is interesting. I didn't actually know this because I never thought to look it up. But I always wondered why gold's symbol is AU, right? And it's because gold's old name is Orus and Auric, right? Neat, neat. I knew it was them. Well, no, there was a car parking, and I predicted that it was you two. So, oh, that happens everywhere. Every single, I don't know if you've been to other campuses, like any of you have been to any other campuses, but every campus has suicide squirrels. Every single one of them. Okay. So, and they'll act really nice. They'll come up to you. And they're like, "Oh, please give me a piece of bread," and they'll bite you, and then you have to kick them, and then, that's how they commit suicide, right? Just saying, squirrels are not nice. All right. So then we have iron. Iron can lose two electrons or three electrons, so that's why it's iron two or three, right? And its special name is ferrous or ferric, right? That's where the Fe comes from. And then chromium can lose two or three electrons, and so that's why it's chromium two or chromium three, and we'll call that chromus or chromic, right? That's all I need you to know about that, okay? I'm thinking I think that in your PowerPoint, if you're looking at the PowerPoint slides, there's like 5 other slides about this in there. I cut them out already, so don't even worry about that. Just know that these metals here can lose 1 or more electrons at a time, okay? So that brings us over to covalent bonding. So before we were talking about when there's the transfer of electrons, like when we were watching Teo Gray and his friend there making salt, right, for their popcorn, they transferred sodium's electron got transferred over to chlorine, and that's what made them happy, calmed them down, right, because they're a happy couple, right? Well, in covalent bonding, there's not so much of a transfer of electrons, but more of a sharing of electrons by two atoms. Okay, sharing of electrons. The two electrons are no longer orbit individual nucleuses, but they are shared equally between two nuclei, right? Shared equally between two nuclei. If the covalent bond is between atoms of the same element, the molecule is formed from the element. The molecule formed is that of the element, right? So these are those diatomics, like hydrogen, uh, and then like chlorine, right? Fluorine, those diatomics. Okay. Covalent bonds, covalent bonds between atoms of different elements for molecules of compounds, like HCl, which is hydrochloric acid, right? Hydrochloric acid. Hydrochloric acid is that muriatic acid I was talking about that one time that they did on whale wars. They throw them at people. Well, not at people, but at whales. Well, not at live whales, at dead whales to spoil their meat. Yeah, there we go. I didn't want no animal cruelty in this class. Okay, so let's take a look at the hydrogen molecule H2 real quick. Okay, and this is a very common graph that you see, plot that you see in chemistry. A lot of people like to refer to this as the van der Waals plot. You don't need to know that, but that's what people like to call it. And what it's actually showing is the fact that when two hydrogen atoms are far apart, because this on the x-axis is distance of the two atoms, when they're far apart, they don't really interact with each other. Okay? But then as they get closer and closer to each other, right? As they get closer and closer to each other, they start to interact. And then there's a point at which their interaction is like perfect and they're at the lowest energy. And so that's when you form a diatomic, right? Hydrogen would rather be down here with another hydrogen, even though it's incestuous, right? Because it's lower energy down here than being separated up here and being at this higher energy. But the problem though is that if they get too close to each other, right? If they get too close to each other, they just bounce off of each other, and then they start to really like not like each other at all, right? And so it starts to go up in really high energy, right? So there's this part right here, this little tiny little dip, this little valley right here in this plot, where hydrogen is most happy at this distance, right? So what is that distance? Hydrogen is most happy when it's 0.074 nanometers from another hydrogen, right? So if you bring a hydrogen atom and another hydrogen atom, and you bring them close to each other, and you get them as close as 0.074 nanometers from each other, they'll become what? An H2, right? They'll become a hydrogen molecule. It's cool stuff because hydrogen, the two atoms of hydrogen are most stable at 0.074 nanometers from each other. So that brings us to our first question of the day. At what distance is two hydrogen atoms the most stable? Well, that was terrible grammar I just said there. I said is to now, yeah. At what distance? No, wait. What is the distance at which two hydrogen atoms are most stable? Right? Is it 25 nanometers? 0.074 nanometers? Is it 36 nanometers? Or is it 74 nanometers? Okay. All right. The vast majority of people answered B, which is correct. It is indeed 0.074 nanometers. Okay. 0.74 nanometers. So this also brings us then to the Lewis structures of covalent compounds, right? So remember in the Lewis structure of the ionic ones, you actually had a transfer of the electron from one atom to the other, right? And you had two different atoms with 8 on one side and 8 on the other, right? But here, right, well, we're using hydrogen, so it's only 2, but normally it's 8, right? Here, you draw both of the hydrogens, right? But then when they're in a covalent bond with each other, they're sitting next to each other and they're sharing those 2 electrons. How cute, right? How cute. It's like they're holding hands. Two hands are holding right there. They're holding hands with each other, right? It's very cute. Very cute. So on your test, you might have a picture of like two people holding hands or something. You'll have to figure out whether or not that's covalent bonding or ionic bonding, right? Or like I said, chlorine stealing electrons away from a kitten, right? That kind of thing. Okay, so here's something that's a little bit more applicable, right? We've got a single hydrogen atom over here with its lone electron. It wants to share with chlorine to make hydrogen chloride gas or hydrochloric acid. And so when you draw that Lewis structure, right, you see here chlorine still has all of its electrons on the right side here, but it's now sharing its electron with hydrogen. So hydrogen has two, that fills its outer orbital. And then hydrogen is sharing its electron with chlorine, and that fills its outer orbital, right? So it's very happy. Both of them are very happy. One's slightly bigger than the other, but that's okay, right? Whatever floats their boat, okay? Whatever floats the boat. So shows the hydrogen and chlorine atoms sharing two electrons. That is a covalent bond. So sometimes chemists will just not even draw the two that are sharing there, because chemists don't have any heart, I guess, or something. They're cold-hearted, and so they don't want to show sharing. So all they do is they delete those two electrons, and now a bond, right, is just like a dashed line right there, right? So you could do either two dots there to represent sharing of two electrons, or make a line. Okay. So stable covalent molecules. Stable covalent molecules form when atoms share electrons in such a way that it gives all atoms the noble gas configuration. So just like in ionic compounds, right? Everybody's shooting to be a noble gas, right? Shooting to have noble gas configuration. Who cares about their charge, right? But for covalent compounds, though, they don't do it by by transferring electrons. They do it by sharing. So that still means, though, that the octet rule is in force, where in forming compounds, atoms tend to gain, lose, or share electrons to achieve electron configuration of noble gases. Okay, so taking a look at the Lewis structures for all these different compounds right here, and we're talking about covalent bonding, right? So covalent bonding is mostly this over here, right? Everything from like 3A and across, and then there's this little stair step thing, right? We call those the metalloids, but there's a little stair steps thing right there, right? So that's that stair step thing right here, that little red dark line on the periodic table. See that red line, right? So everything past the stair step thing right here, right, is a nonmetal, right? And nonmetals tend to do covalent bonding, right? They tend to do covalent bonding. And the interesting thing about covalent bonding in nonmetals is the fact that they tend to have they can form a certain number of bonds. For example, of course, noble gases, right? Group 8A already got their octet. They don't form any bonds with anybody, right? They're so noble, the nobility, right? And then hydrogen and group 7A tend to form one bond, right? So hydrogen in group 7A is that group right there with fluorine, right? And remember, fluorine, chlorine, and bromine, they're missing an electron, correct? So they are capable of basically sharing one bond, right? Sharing one bond. Group 2A is capable of sharing and having two bonds, right? Oh, sorry, 6A is, sorry, let me say that again. Group 6A tend to form two bonds. And so you know that because that's grouped with oxygen, sulfur, right? And oxygen and sulfur both have a -2, right? And so that means they can share two bonds, okay? Group 5, which has nitrogen in it, can do three bonds. And then group 4, which has carbon in it, can do four bonds, okay? So let's look at that in picture form. Okay, so here we go. So group X, group X, group 8A here. X is the element, I guess, or the atom, right? And it doesn't need to form any bonds because it's got eight electrons. And the example there would be neon, right? The example there would be neon. Okay. Then we have 7A, which includes chlorine, fluorine, bromine. They have 7 electrons, right? They're missing one. That means that they can form one bond. So that's what it looks like when it forms one bond, right? 6A, which has oxygen in it, right? Sulfur in it, has 6 electrons in it, so it's missing 2 electrons. So when you're missing 2 electrons, how many bonds can you form? 2 bonds, exactly. So here's oxygen with 2 bonds, which makes a lot of sense because you can put an H there and an H there, and what do you get? Yes, water. You get water, right? Literally, you put an H there and you put an H there and you get water, H2O. Group 5 contains nitrogen, right? And so it has 3 bonds it can share with, right? Because it's missing 3 electrons, okay? And then interestingly enough, if you put 3 H's here, one there, one there, one there, you get ammonia. It's what we use to clean our glassware, right? Or windows, right? And then last but not least, we have group 4A, which has 4 bonds, right? Because it only has 4 electrons, so it needs to be a bond for each one of those electrons, okay? So a question that I may ask you on an exam, which won't be for a while because we're about to have Thanksgiving break, right? A question I might ask you on an exam would be, which of the following elements can have 2 bonds? Or which of the following elements can have 3 bonds? That kind of thing, okay? Simple things like that, okay? Any questions so far? This is a pretty self-explanatory chart here, right? You memorize that chart, you're golden, okay? You're golden. All right, so now we have double and triple bonding, okay? So sometimes, right, when an element has 2 or 3 or 4 unpaired valence electrons, its atoms will sometimes share more than one of them at a time with another atom. And this is called a double bond or a triple bond between 2 atoms are possible. They're possible. And we'll take a look at that in a second. We'll take a look at that in a second. But you can also have a triple bond and a double bond too, not just a single bond. We'll look at that one just 1 second. So our next question is then sulfur will tend to form how many bonds? Right? So look at the periodic table, look where sulfur is, and figure out how many bonds it can form. I'm at 19, so I'm waiting for 2 more responses. 20, one more response. 21. Woohoo! All right. 19 out of the 21 of you responded correctly. The answer is indeed 2. Why is it 2? Exactly. It's just like oxygen, and it's missing 2 electrons, right? See, chemistry is simple. You thought it was complicated? It's very, very simple. Like all the answers are on the periodic table, literally. That's your cheat sheet. I always tell students, your best cheat sheet in chemistry is the periodic table if you know how to read it, right? So let's take a look at double bonds and triple bonds, okay? So we have a molecule here called CO2. It's that same molecule that I told the FedEx lady that you breathe out, right? That molecule right there, right? Frozen CO2 you can use to ship, steaks and stuff, but for some reason FedEx thinks it's dangerous, even though you breathe it out. Okay, but CO2, in order for CO2 to actually have a structure that has all the atoms have 8 electrons, right? All the atoms have 8 electrons. It has to share some twice. And so that's called a double bond here. So here's a little structure of, whoa, that's confusing here. I thought that was an electron, but that's a bullet. So don't count the bullets. Don't count those bullets, okay? Don't count these bullets right here. Those bullets look like electrons. They're not electrons. Those are all bullets. So don't count those. So here's oxygen right here, and it's got 6 electrons, right? And then here's another oxygen that has 6 electrons, which is consistent with what the periodic table tells you. Then we have carbon here, right, with 4 electrons, which is again consistent with what the periodic table tells you. Okay. Well, if you were only to form one bond, right, between oxygen and carbon, and another bond here between oxygen and carbon, you would still have 2 electrons that are left over, right? And you'd only have 6 electrons for carbon. Does that make sense, right? So, poor carbon, it needs more. Unless if you don't give it more, it's not going to be happy. So, oxygen being the nice guy it is, right? Both of these guys, they're going to share more than one electron with the carbon, right? Where now you form a bond with carbon here, right? And then you form another bond with carbon there with those 2 electrons. So now you have a double bond just like this, right? Because now you're sharing two pairs of electrons. And then the oxygen on the other side can do the exact same thing. It can connect those two electrons right there, and then it can connect these two electrons over here, right? Or maybe those two like there and those two right there, right? And so now that's called a double bond, right? And so we signify double bonds in chemistry by just having two pairs of electrons in between, right? So there's a double bond there, double bond there, double bond there. Or we can do it this way here where we just put two lines. It's easier to see two lines. So I would probably just draw two lines there, and that would signify your double bonds, right? And when you do that, you notice now both oxygen has 8 electrons, right? Two here, and then two there from one bond and two there sharing from the other bond. Carbon now has 8 electrons, right? Two there from that bond, two there from that bond, two there sharing from that bond, and two there sharing from that bond. And then the other oxygen also has 8 electrons. Two up here, two from there, and two from there, right? You see how their sharing makes everybody happy? Sharing is caring, Barney says, right? Sharing is caring, okay? And so, see, and so covalent bonds are much more, I guess, affable than ionic bonds are, or ionic compounds, because ionic compounds are about give and take, right? Very selfish, right? Sometimes they give and they take more than once, right? Multiple times, okay? But in covalent bonding, sharing is caring, right? So that's a good way to remember it. Sharing is caring is covalent bonding. And so caring starts with a C, and so does covalent. Helpful. That's helpful, right? What's a good one for ionic bonding? Ionic bonding. Um, I'll have to come up with a different one for ionic bonding. Anyway, so this is what it looks like in real life here. We've got carbon right there, right, with its electrons in its outer shell, and then we have oxygen here with its electrons in the outer shell, and they overlap, so they share, right, and they stick together, right, and they form the molecule that you breathe out every second of the day, right? We can also do triple bonding. We can also do triple bonding, right? Because again, covalent bonds, they like to share, right? So recall that nitrogen, right, needs 3 electrons. Okay, it's missing 3, and it can form 3 bonds, right? And if you were to put the two nitrogens next to each other and only form 1 bond, right there, you still are missing 2 electrons, right, from the octet. Okay, all right. And if you're missing 2 electrons from the octet, nitrogen's not happy. This nitrogen's not happy. Everything's better when they're sharing, right? And so nitrogen here will share 3 pairs of electrons, right? And so that's going to make the octet for nitrogen. Because notice, if you just look at the nitrogen on the left side here, there's 8 electrons, right, that are sharing. And then if you look at nitrogen on the right side here, there's 8 electrons, right? 6 of them are sharing. Sharing is caring, right? Good stuff. Good stuff. Okay. So here's how we would draw it chemically with 3 lines. So double bond is 2 lines, single bond is 1 line, triple bond is 3 lines, all very self-explanatory, right? And this is how it would look in their shells, right? We have nitrogen there, nucleus there, nitrogen nucleus there, 2 electrons over here, 2 electrons over here. They're not sharing, but then you have 6 electrons in the middle that are sharing, so that both nitrogens have 8 electrons, right? Both nitrogens have 8 electrons. It's so copacetic. It's so copacetic. I still haven't come up with a good way to remember ionic yet. I think that the sharing is caring is covalent thing works pretty well. Um, Ionic bonding, transfer, give, take. No, none of that's fitting. Not working. Not working. You guys think about that. Come up with something to remember. I'm counting on you, Shanice. Come up with something that that will help with the remembering what ionic bonding is. Unless you already know what it is, and you don't have to come up with one, right? Because I've flogged that dead horse many times now. Okay, so draw and use don't use the board. Okay, this is just drawing Lewis structures, right? There's chloroform, Oh, it's telling you to draw them. Don't worry about that. Chloroform, that's easy, right? Because carbon is in the middle with an H and three. I don't even want you to have to do this, honestly. So don't even worry about that. Don't worry about drawing them because I'm never going to ask you to draw them, okay? And then, oh, here we go. This is what I need to see. All right. So covalent bonding, miscellaneous information. Unlike ionic bonds, covalent compounds are composed of individual molecules with a specific formula, right? So for example, we have here carbon tetrachloride, right? And carbon tetrachloride is a carbon with four chlorines around it. It makes sense because carbon can form four bonds, right? Chlorine can form one bond, okay? And so put them together and you get carbon tetrachloride. And so carbon tetrachloride, the molecule, or not the molecule, but the chemical, right, consists of many individual molecules of carbon tetrachloride, okay? So within the molecule, the covalent bonds are strong, right? So the bond between carbon and chlorine is strong. But the individual molecules are only weakly attracted to each other. And so what that means is that things that are organic or things that are covalent have very low boiling points, very low melting points, okay? And you know this from, for example, when you see gasoline on the ground, it evaporates, right? Or you spill your beer, well, not beer, it doesn't work with beer. It works with Everclear, right? You spill your Everclear on the table, right? Which it's a bad thing to be drinking Everclear by itself. But if you're taking shots of Everclear because you had some bad chicken or something, right? By the way, did you know that? Did you know that if you eat bad chicken, like undercooked chicken, like you could get like salmonella poisoning and then your eyes bleed, right? So to prevent that, I highly recommend taking at least 2 shots of Everclear. It's perfect because then you literally kill the salmonella, right? It won't go attack your eyes. Why did we talk about that? God, I'm so tangential today. Does anybody remember why I even brought that up? Oh, thank you. That's what it was. Yes, if you spill your Everclear, right? It's actually a covalent molecule, Everclear is. And so when you spill it, it actually evaporates. It dries really fast, right? It's the same reason why when you get your wipes, not necessarily the Lysol wipes, but the other ones that are like ethanol based, because these are like, I don't think these are ethanol based. Are they ethanol based? I don't think they are. But if you use the other ones that are ethanol based and you wipe down your table, it dries almost immediately. It's because it has a very low boiling point, right? Because it's covalent, right? And so that's why. So funny thing is that the ethanol molecule itself is a strong molecule, but its attraction to each other is very weak, and that's why it evaporates so easily, right? Good stuff. Thank you for bringing me back on track, because I definitely went off track there. Yeah. So yeah. Okay. Then, oh, here we go. Which of the following is not true about covalent compounds? Covalent compounds are composed of individual molecules with a specific molecular formula. That sounds reasonable. Covalent molecules are strong molecules, right? Or individual covalent molecules are strongly attracted to each other. Wink, wink, right? Or all of these are true. Okay, or all of these are true. Ouch. All right. I'm still waiting for 3 responses. 3 responses, please. 2 more responses. 2 more responses. 1 more response. I'll just go ahead and show it to you because we're at 20 now. I'm a little disappointed. I thought that my nasty eyes Everclear story would have gotten a correct answer out of this question, but that's okay. Most of you did create it correct. Individual covalent molecules are not strongly attracted to each other. They're actually very weakly attracted to each other. And that is the reason why they evaporate. I even made it big for you. So what you're saying is my story had an impact. You just read the question wrong. Okay, that's all I need to know. That's all I need to know. All right, so let's ask the question then. Ionic and covalent? So some compounds contain both ionic and covalent bonds, like sodium hydroxide here, which is a very strong base, right? If you've never heard of sodium hydroxide before, it's also known as lye. And they use lye to do a whole bunch of things like cleaning and stuff like that. But I think the most common thing that people use lye for is to coat the outside of large pretzels to make them have a very good crispy outer shell and very doughy on the inside. So have you ever wondered how you get that nice pretzel that you get from the movie theater that you dip in cheese, or the ones you get at the baseball park, right? They dip it in lye. Okay. Don't worry, it's all gone when they're done cooking it because you don't want to swallow it. That'd be a bad idea, right? I actually learned that from Alton Brown, right, from Food Network. Didn't know that was a thing. But anyway, so funny thing about it is that hydroxide, this guy here, that guy's covalent, right? So in its own, we call this a polyatomic because it has more than one atom in this covalent bond here. And then since it's got a negative overall charge, it can actually share an electron with what? Or not share, transfer an electron with what? Sodium, right? And so that's how you get sodium hydroxide. So this guy here, sodium hydroxide, is both ionic and covalent. Man, that's crazy. That's crazy. So the thing that you'll need to do is be able to predict whether or not a compound is ionic or covalent. So here's some general rules for you to take a gander at, because I don't want to leave you hanging, right? Don't want to leave you with no help at all in this situation. First thing to note, compounds formed of only nonmetals are usually covalent. Okay? The only one that's not covalent are ones that have ammonium in them, which is NH4, right? That's the only one that's not. But this here, the vast majority of compounds that are formed with just nonmetals, they are definitely covalent. Vast majority. Just one, ammonium, is not going to fit with that. Okay? Compounds of metals and nonmetals are generally ionic, which you knew that already before, right? I keep on telling you the story about sodium chloride, and sodium chloride is an ionic compound, right? Right? Compounds with metals with polyatomic ions are also ionic, right? So that would be sodium hydroxide that we saw in the previous slide. Compounds that are gases and liquids, right, or low melting point solids are definitely covalent, right? Because we said that a second ago, covalent compounds, while their molecules themselves are very strongly held together, right, with the bonds, their attraction to each other is not as strong, and that's why your Everclear evaporates when you spill it. No, don't evaporate. Let me look it up. No, I mean, why wouldn't you? I mean, Everclear kills all the germs, right? So why wouldn't you look it up? Right? I'm more of a Captain Morgan person myself, but whatever. But if Captain Morgan were to spill on the table, I wouldn't lick that up. That's not strong enough to kill all the germs on the table. Only Everclear is strong enough to kill all the germs on the table, and then I would lick it. Okay, that's a really weird thing to say. Anyway, so then compounds that conduct electricity when melted are generally what? Ionic. Which you talked about that before with sodium chloride again. I think that sodium chloride is our quintessential ionic compound, right? Quintessential ionic compound. Do 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 do. Okay, so let's take a comparison. Let's look at and compare. Uh, we can compare now the properties of ionic compounds and covalent compounds. This is one of those I like to call the you welcome charts because it tells you things you need to know for an exam, and I'm giving it to you now. So you're welcome, right? You're welcome. It's just like in the movie, Moana, right? When the rock comes out, and he's like, "You're welcome." You know that one. You know what I'm talking about in Moana? Yeah, that one. Okay, just making sure everybody knows what I'm talking about here. I didn't make up Moana. Okay, good movie by the way, great movie. You know, the Rock is quite hilarious in there, right? So anyway, what's his name in the movie? Maui? I believe it's Maui. Yes, it's Maui. I actually, in my previous classes or in my other class, whenever I give them a chart like this, I actually play the song first, and then they get to see the chart. So, anyway, I should have done that with you guys. I'm sorry. I feel like I'm leaving you out now. It's like the whole FOMO thing now, fear of missing out. You've missed out on the song. You missed out on the song. Okay, so we have ionic compounds here, and we have covalent compounds here. Notice ionic compounds are made of crystalline solids, right? They have high melting points and high boiling points, which makes sense because I told you before that salt takes like, what, 600 degrees to melt? Something like that. It's crazy. They also conduct electricity when they're melted, right? And many are soluble in water, right? But they're not soluble in nonpolar liquids. So if you throw salt into like gasoline or something, it's not going to evaporate. Or you throw salt into oil, it's not evaporate, I'm sorry, dissolve. You throw salt into oil or gasoline or something, it's not going to dissolve. But salt will definitely dissolve in water because it's super soluble in water, right? On the other hand, we have covalent compounds. These guys are gases, liquids, or solids, right? But notice that they're not crystalline solids, okay? They're just solids. So a good example of a solid would be like butter, right? Butter is a covalent solid, okay? They have very low melting points and boiling points, right? Uh, a good example of that, butter, right? Because you can really burn butter real easily, right? So and then it just turns black, and then the smoke is everywhere, and you're thinking to yourself, man, I really wish I'd gotten some of that ghee, you know, ghee purified butter, clarified butter, because it has a much higher smoke point and still tastes like butter. Then you can put it on your popcorn; it tastes great too. So, yeah, I should get some more ghee. I should get some more ghee butter. I think that's only available at like Aldi too, right? Or maybe it's at Whole Foods. Anyway, poor electrical conductors makes sense, right? That makes sense that they're poor electrical conductors in all phases. Why? Because there's no metals in nonmetals, right? Makes sense. There's no metals in nonmetals. And then lastly, many soluble, many are soluble in nonpolar liquids, but they're not soluble in water, which is obviously apparent when you put oil into water and they're not miscible. They don't dissolve in each other, right? So yeah. All right. Here's your next question. Which of the following properties of ionic compounds is not true? Kunji, it says not. Just letting you know. Crystalline solids are made of ions, right? Sorry, I shouldn't be telling you. Melting points, high melting points and boiling points, does not conduct electricity when melted, and many are soluble in water. Okay, so where is that one at? There we are. I'm happy to see that 90% of you are at least paying attention to the question and the lecture. Can you believe this is our third to last lecture? I mean, really. I mean, it's almost over, guys. It's almost over. You're never going to have another class like this, except if you take me again. So, still waiting for two people to answer. Who? Oh, dang. And then somebody back there left too. Okay, maybe that's who it was. All right, so again, like I said, like 90% of you got that correct. The answer is indeed C, right? Because does not conduct electricity when melted. That's incorrect. It does conduct electricity when it's melted. Okay, does. So where's my laser at? Does conduct electricity when melted. Okay. Okay. All right. So here's some predictions. Let's predict some types of bonds, right? So we have here, this is potassium and fluoride, right? Pretend you can't see what that is. What is that? What kind of compound is that? Ionic, exactly. Good job. Yeah, see, good job. Okay. Then we have silicon and hydrogen, right? Silicon and hydrogen. Again, pretend that that's not there. What is that? Covalent, exactly. It's definitely covalent. Good job, right? Because silicon and hydrogen are both all what? Nonmetals, right? Nonmetals, okay? Then we have here calcium nitrate. What is that? The answer is up there, but you know, it's definitely ionic, right? This part right here, the nitrate part is not ionic. That one's covalent, but the compound overall is going to be ionic, right? The compound overall is going to be ionic, okay? Because you have a metal and it is combined with a polyatomic ion, and all the polyatomic ions are what in this? They're all nonmetals, right? And so when you put a metal with a nonmetal, it's always going to be what? Ionic, okay? Then we have neon. What the heck? What's X? Oh, just a random gas. I get it. See, I don't know if I told you this, but I've never actually seen these PowerPoints. I just, as they come up, I'm like, oh, what is this? And I just explain it to you. So I'm kind of winging it up here, right? The only thing I see beforehand is the questions I make for you, right? So yes, X is some gas at room temperature. So if it's a gas at room temperature, gases are all what? They're non-metals, so they're all what? Covalent. Exactly. Okay. Okay. And then we have Y here is something that melts at 900 degrees, holy mother, right? And then it also conducts electricity. What is that? It's ionic because, for example, salt melts at like 600, 700 degrees, and it also conducts electricity when it's melted. All right, let's try a couple other ones, okay? We got phosphorus and chlorine, right? So phosphorus is a nonmetal, right? Chlorine is also a nonmetal. So what is it? Two nonmetals make it covalent. Yes, whoever said that, good job. This is so easy, isn't it? So easy. Just pretend that the answer's not there, but like actually have the answer there, right? And maybe I'll just put my hand over it while you're taking the test and be like, "What is the, what is the answer?" Right? And then we have magnesium fluoride here. What is magnesium fluoride? What is magnesium fluoride? Yes, it's ionic because magnesium is metal, right? And fluoride is what? Non-metal, right? It is as simple as that. Like quite literally. It is as simple as that. Okay? So now that you know so much about covalent bonding, right? It turns out that you can have two types of covalent bonding. One type is called polar covalent bonding, and the other type is called nonpolar covalent bonding. And it's exactly as it sounds. Okay? Generally, what happens is that if you have two atoms together in a covalent bond and they're different, it's going to be polar, right? Just like a magnet, right? Has a north pole and a south pole, different poles, right? For a molecule, same thing. Two different poles, right? They're going to be polar. But if you have a molecule that has two of the same atoms next to each other, what are they going to be? Non-polar, right? Because they're the same on both sides. Okay? So remember that in covalent bonding, electrons are shared, but these bonds are not always equally shared. Okay? Unless some atoms are the same element, the bonding electrons spend more time around the more non-metallic element. Okay? The sharing is unequal, and this is called the polar covalent bond. Okay? Polar covalent bond. So what that indicates then is that one side is slightly positive and the other side is slightly negative. Right? Why is that? It's that way because there's this thing called electronegativity. Okay? So this is one of those things I wanted to share with you as far as the trend of the periodic table goes. It's called electronegativity, and it's a measure of the ability of an atom to draw electrons to itself, right? Electronegativity is an atom's ability to just pull electrons away, right? And it turns out that when you look at the periodic table, the more to the right you are and the higher up you are on the periodic table, specifically this corner right here, the more electronegative you are. So tell me right now, except for the noble gases, what is the most electronegative atom on the periodic table? Fluorine, exactly. Fluorine is the most electronegative atom on the periodic table. Okay? So the more to the right you go on the periodic table and the more up you go on the periodic table, the more electronegative it is. And so the more capable that atom is of just just hoarding all these electrons. Okay, good stuff, right? So here's another example, right? We have hydrogen, which is on the left side of the periodic table, not very not very electronegative, correct? Right? But then it's being connected to chlorine, which is on the right side of the periodic table. Is chlorine electronegative or not? Super electronegative, right? Super electronegative. So that means this is a nonpolar bond, right? And so hydrogen and chlorine are stuck together like this. And then us chemists like to draw this little arrow with a plus sign here showing that electrons are being drawn towards the chlorine. So the arrow actually points at the most electronegative atom here, which is chlorine. Okay? Good stuff, right? So here's what I was showing you before, right? On the periodic table. You notice how we just cut out all the transition metals because we don't care about the transition metals, right? We just don't care about the transition metals. And so when you cut them out, you see that when you go towards the right and you go up, right? The most electronegative atom is what? It's fluorine, right? Chlorine's pretty up there too. Oxygen's even more electronegative, right? Good stuff. Good stuff. Okay, good stuff. So practically then what we see is this, right? We've got two atoms, right? And if the electrons are transferred, then we have it as ionic bonding, which we already know. Okay, we have it as ionic bonding, we already know that. Okay, but then over here, if we have two atoms and they start to share, that's called covalent bonding. And if the electrons are shared equally, that's called nonpolar covalent bonding, right? But if the electrons are shared unequally, that's called polar covalent bonding, okay? And again, the vast majority of the time, if you have a nonpolar covalent bonding happening, it's because there's two of the same atom next to each other, okay? And then if you have a polar covalent bond happening, right, that means that you have two different atoms next to each other. In this case, it could be a fluorine over here and a hydrogen over here. Does that make sense? It's good stuff. It's good stuff. Okay. So again, I want to show you how we denote this in a molecule, right? So here's water, right? This is H2O, okay? And here's the oxygen H2O. And remember, oxygen is quite electronegative. So it will pull electrons away from hydrogen and away from hydrogen. Even though they're sharing, it's unequal sharing. And so the way we draw it is with this arrow here with the plus sign showing that electronegativity is being drawn towards, or electron density is being drawn towards the oxygen from both of those, right? So if I were to ask you this question, for example, which side is the most negative side and which side is the most positive side, right? Which side is the most negative side? The side with the oxygen on it, right? Because that's where all the electrons are, right? Because electrons are really negative, right? And which side's the most positive side? The hydrogen side, because that's the one that's not electronegative, right? So you can see now why this is a polar molecule, right? With a polar covalent bond, because you have a negative charge on this side, right? And then a positive charge on this side, and it becomes a polar molecule. Okay. So here's another example, though. Check this one out. This is one of those times when it doesn't have to be two of the same atoms together to make a nonpolar covalent bond. Because here we have a carbon, but then you have chlorine in equal positions, equal distance all the way around carbon, right? With the same angles, right? 109 degrees to be exact, right? And so now the electron density is being pulled away from the carbon in four directions, but an equal amount of space, right? So this here would be a nonpolar covalent bond, right? Because not one side is all negative or one side is all positive. Does that make sense? Right? You can see that it's an equal it's an equal robbing, I guess it would be, of carbon of its electrons. All four of these chlorines are just robbing this carbon of its electrons. Okay, all equally, right? So let's see here. I'm getting close to where I want to end, right? Okay, so polar bonds and polar molecules. Molecules as a whole, as well as bonds, can have polarity, right? A molecule is polar even if electrons are more attracted to one end of the molecule. Okay? So such a molecule has a slightly negative end and a slightly positive end. That's our polar covalent bond, right? And then this type of molecule is said to have a dipole or to be a polar molecule, which we said that just a second ago. Okay? So here's a really good picture here, right? Here's hydrogen chloride again, or hydrochloric acid. Notice how most of the negativity is over here with the chlorine, and that's why the electrons are all floating around over here, and poor old hydrogen there's all by himself, right? All by himself. Okay. Um, so here we go. Look at this guy here. We've got a nonpolar molecule here with beryllium in the center and hydrogens on either side, right? So one of the things you could say, if I were to give you a molecule and I'm going to ask you if it's polar, nonpolar, or whatever, is that if it's symmetrical, it's nonpolar, right? But if it's not symmetrical, it's what? Polar. That's a good way of looking at it, right? Because even with this guy over here, the one that had this guy, this guy is symmetrical, right? And since it's symmetrical, it's nonpolar. So remember that. If it's symmetrical, it's nonpolar. If it's non-symmetrical, it's polar. Anyway, so water. See, if water were linear, right? If water were linear, it would be nonpolar, but it's not linear. It's actually bent like this, right? And since this is bent, this is the one case where, since it's not symmetrical, well, actually, it's symmetrical, right? But it's still polar, okay? So water is like the only exception, okay? Water is the only exception. So this is where I'm going to end the lecture soon here. Two more slides. This is a summary of polar bonds and polar molecules. If the polar bonds in a molecule are nonpolar, the molecule can only be nonpolar. That makes sense. A molecule with only one polar bond has to be polar, and then a molecule with more than one polar bond will be nonpolar if the shape of the molecule causes the polarities of the bonds to cancel. Otherwise, it will be polar. So the last thing I want to show you, right, is this picture here. Check this out, okay? So I feel like I'm always showing you things with electricity and like static electricity, moving things, right? And so this is a stream of water, right, which is a polar molecule, right? And it's a stream of water, and it's bending because there's a pole here, like a little stick or pole or pipe that someone's rubbed a lot, so now it has static electricity on it, right? And it's actually drawing the water and bending it, right? And it's not going straight anymore. But this same little probe or whatever the stick here or pipe here doesn't do anything to the stream here because the stream here is carbon tetrachloride, which is a nonpolar molecule. So notice that polarity does happen, right? And you can actually affect the stream of molecules if you place something that's electric, like static electric, next to it, right? It will draw away, deflect the stream of polar molecules, but it will not deflect the stream of nonpolar molecules. You see the ramp up there and then the slow to thing there? Yeah. That ends today's lecture. That ends our chemistry lecture. Thank you very much.